Matrix operations. Okay, let's dive right in. So let's start with addition of two matrices. So if I have, actually let me use A and B. If I have two matrices, A plus B, I can add them together to get another matrix. And this works pretty much exactly the way vector addition works. So if I have, if I have a matrix 1, 2, 3, 4, 5, 6, and I add together the matrix 0, 1, 0, 1, 1, -1, just making up some numbers here, trying not to make it too hard on myself, then I just go by element wise and I add them all together. So I would say 1, 3, 3, 5, 6, 5, right? And in general, if you have some matrix C that is equal to A plus B, then that means that Cij is just Aij plus Bij, each individual element being added together. And they have to be, as with vectors, they have to be the same size. In this case, they're both 2 by 3. Can't add together matrices that are not the same size. And just as with vectors, the sort of usual rules that we would want to apply. A plus B is equal to B plus A, that it's commutative, right? And it's associative. If you have A plus B plus C, it's going to be equal to A plus B plus C, all the things that you'd expect, right? Adding the zero matrix doesn't do anything, right? All of those nice facts work exactly as you'd want, exactly the same as they do in vectors. And similarly, matrix scaling a matrix by a real number works in the exact same way also. If I have some real number A or real number alpha and I multiply it by a matrix A, that matrix, the ij element of that matrix is going to be alpha times Aij, right? So, for example, if let's say I had 4 times I, and let's say that this is I3, right? What would that be? Scalar 4 times I3. Think about that for 1 second. Pause the video if you need. You should get 4, 0, 0, 0, 4, 0, 0, 0, 4, right? Because the identity matrix is just 1s down the middle, just multiply the 4s. There you go. Okay, so addition and scaling work pretty much exactly the same as they do in vectors. We do have a new operator, which is the transpose operator. So if you have some matrix, I'm gonna go over here. Okay, so all this was adding. Let's go over here and let's do transpose. So we say A transpose Ij is A Ji. Okay, so if I have a matrix that looks like 2, 0, 1, 3, 1, 2, and I take the transpose of that matrix, I'm going to flip it so the rows become the columns and the columns become the rows. So I end up with 2, 0, 1, 3, 1, 2. That was supposed to be a 2. Right? And you can see, for example, if this, if this was A, then A21 would be that guy, which is the same as A12, that guy, right? Flipping them. And this, because of that, the dimensions of it flip also. So if A is an M by N matrix, then A transpose is going to be an N by M matrix, right? Because number of rows and columns flip. If you take the transpose of a matrix and then take the transpose of the matrix again, you get back the original matrix, right? And in general, if you have anything, if something is true of the columns of a matrix, for example, then it's true of the rows of the transpose of the matrix, right? So, so let's say I told you that the columns of A were orthogonal, then that would mean the rows of A transpose were orthogonal, and so on. If a matrix is equal to its own transpose, so if A is equal to A transpose, then that means the matrix is symmetric. So what would that look like? Well, for example, 2, 1, 1, 2, like this. That's a symmetric matrix, right? You can make a bigger one. All identity matrices are symmetric, of course, but it doesn't matter what any of these elements are, so long as the rows and columns are the same, right? So that so long as Aij is equal to Aj for any ij, this is a symmetric matrix. And just as a little side note, in the same way that a triangular matrix, you could sort of like save a little bit of work by only storing the triangle. If you know that a matrix is symmetric, you can also only store the triangle, right? Because if you note symmetric and say, the upper right triangle, then you don't need the lower triangle, right? Yeah, that's symmetric. Okay, so we did matrix addition and scaling. We did transpose. One other thing that we may come across here and there is matrix norm, and we're going to define our matrix norm exactly as if it were a vector norm. So we're going to do the sum of the square root of the sum of the squares of all of the elements, because there's two indices to go over here. I might write something like the sum from I equals 1 to m of the sum from j equals 1 to n of m ij squared, and then that whole thing to the 1/2. If you wanted to write using the sort of dot notation, it's a little bit trickier. We haven't talked about. Oh, I'm just assuming that this is an m by n, right? M by n matrix, lowercase m. It was fairly convenient for us to use the dots for our sums with vectors. It's a little bit harder. I mean, I need something like, I can say like m11 plus ... Can't get my dots to go. Plus plus m1n. See, I even have to think about it. Plus ... m little m 1 plus dot 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 plus m mn. I maybe should pick different letters, not use m for both, but there it is. So this sort of 2D sum, it's a little harder to express just using the dots, but the idea is the same. And this won't, I think, come up quite as often as the vector norm comes up, but it will come in handy for us to be able to do this. And we might, for example, want to say, to talk about like the distance between two matrices. I am going to switch. I'm going to call it A instead. So, the norm of A minus B, meaning the distance between the two matrices, which may come up in a particular context if you want to know if they're close or something. And as with vectors, there are other kinds of norms, and this one actually is called the Frobenius norm, and we write with a subscript f. I'm not even 100% sure I can spell his name right. Frobenius. I might cheat and look if I can find it. Yes, I got it right. Yay, okay. Yeah. But we're not going to cover any other norms in this book, and this is the one that will be, so you don't necessarily need to even remember that name or anything, but just if it does come up somewhere, this is the Frobenius norm. Right. So just kind of like overview basic matrix things. Addition and scaling work exactly the same as vectors. Transpose flips the rows and the columns. Matrix is symmetric if it's its own transpose. And norm, will work the same as vectors. We'll square all the elements, add them together, take the square root. And those are our sort of basic matrix operations. Now we can get into the really exciting, the multiply.